Okay, yeah, no, I think it's okay. Okay, so thank you very much for inviting me to this seminar. It's always a pleasure to share the results of our research and also to be present in some US universities, even if it's remotely. Just a brief presentation of myself. Indeed, it's a remote seminar because I'm sitting in Barcelona. This is the view of Barcelona from the mountains towards the sea. Barcelona is a nice city, but in this picture, I think it's even nicer than it actually is. And then this is another picture from the city, from the sea towards the mountains. So Barcelona is between the sea and the mountains. And Universidad Autónoma de Barcelona, my university, actually, and surprisingly enough, is not in Barcelona. It's behind these mountains that you see in Barcelona. There is a valley, a kind of suburban valley with the industries and medium-sized cities. And in this area, this is where the university it's found. This is a view of the university. Universidad Autónoma de Barcelona is a general university. It has all types of studies, medicine, law, economics, humanities, and also science and engineering. The School of Engineering is about 15% of the university in size, and basically contains studies of telecommunications, as we said here, electrical engineering, electronic engineering, computer science, chemical engineering. And inside the School of Engineering is where my lab is found. I started this lab or this research group, as we say here, in 2006 to start or to boost the research and teaching in signal processing, because at that time the new degrees on telecommunication engineering, electrical engineering were created at this university. My group is formed by two professors, Jose Antonio Lopez Salcedo and myself. At this moment, we have two postdoc researchers, 4 PhD students, and 2 project engineers. I think you already summarized or explained very well my view, so I don't need to repeat it here. So I think we can move to more technical aspects. And before entering into the topic of the talk today, which is 5G, 6G technologies for positioning, I just want to mention what are the research topics on which we are working on the group now. We have a series of research topics on GNSS, on global navigation satellite systems. This is my, let's say, background. I did my PhD on GNSS, and I worked for several years at the European Space Agency, like the NASA, but in Europe. And in GNSS, we are working on 3 topics, I would say. One is to enhance the security of GNSS positioning with anti-spoofing techniques, with signal authentication and also signal encryption. We are working on array processing for multipath spoofing and interference mitigation, so how to use antenna arrays in GNSS receivers to find out the directions of the multipath components, the possible spoofers and interference, and also how to null them, exploiting that you have, as I said, several antennas on the receiver, but also antennas with different polarization. So try also to discriminate the signals in polarization. And we are building some, let's say, cheap platforms based on USRPs to do angle of arrival estimation of the GNSS signals and also of the 5G signals. So these are, let's say, lab low-cost platforms for angle of arrival estimation. Then a topic that is attracting a lot of interest nowadays in the navigation community is the LEO PNT. So it's the deployment of LEO constellations of LEO satellites for positioning. We are working on this topic, basically on the design of future LEO PNT systems, more specifically on the design of the signals and the receivers for these LEO constellations. These signals can be, let's say, similar to GNSS signals, but they have additional problems that have to be tackled with, because due to the much higher dynamics of the LEO satellites, so higher Doppler and Doppler rate. And also we are studying, and we have proposed new signal formats based on LoRa, signals similar to the ones used in LoRa, the chirp space spectrum, or the OFDM signals, these 5G non-terrestrial networks. We have a tutorial on this topic on the incoming ICAS this year. And then we are also working on 5G, 6G technologies for positioning. It's only one bullet here, but maybe this 5G, 6G technologies for positioning is maybe 1/4 of our activity, roughly. And this is the topic for today. This is just a picture that I have been using in some presentations to illustrate what is a use case where 5G, 6G localization is meaningful. And it's a situation where GNSS would not work properly because you are the car is in an urban canyon and has poor visibility of the sky, so there are no enough GPS satellites or GNSS satellites visible, and also if they were visible, probably the accuracy would not be enough. So our 5G, 6G localization work is has taken this scenario as sometimes as the starting point. So we have a car that has potentially an array of antennas on the roof or in different places, and we want to locate a computer that is determining the position of this car and also the attitude of this car, the orientation of this car. On top of that, we will not only to locate the car, but also locate the other cars or other objects that are around. So we would like to have sensing capabilities in the system. So the question is whether this is possible, if it's possible to do that even when the line of sight is blocked. The line of sight from this multi-antenna, multi-beam base station to the car. And a recent element that has been introduced in this scenario by us and by many other people is the use of smart surfaces to shape the propagation environment. So how we can take advantage of these new components for localization. Okay, an even more futuristic case is this one. Maybe this is what we should target in the future. So we should be able to locate all these cars in this scenario with very poor visibility of the sky and a lot of cars crossing in front of each other. This is really challenging. One could think that with communication technology nowadays, communication between all these cars could be possible. It doesn't seem something unfeasible, but to have these cars driving autonomously, relying on a positioning system, this really seems not possible today. So this is why further research is needed. In a more specific terms, the requirements of different use cases have been studied in many projects and reports, and there seems to be an agreement that for the most demanding applications, like autonomous driving, augmented or extended reality, also robots and cobot interaction, location accuracy better than 1 centimeter is needed, an orientation accuracy better than 1 degree, and a very low latency in the computation of the position that has to be better typically than 10 milliseconds and sometimes only 1 millisecond. There are even more demanding cases where it is said that location accuracy should be in the order of 1 millimeter. But well, I think that for the time being, a really challenging but reasonable scenario is to aim at accuracies of on the order of 1 centimeter and orientation accuracy of 1 degree and update rates of a few milliseconds. The cellular systems, the 3GPP systems, they have been advancing in this direction. We had the 4G system where the main target was to fulfill the emergency call requirements, the 911 or 112 in Europe, with providing accuracies on the order of tens of meters. 5G systems set as target accuracies of the order of 1 meter. And now many studies have been done in the different releases of 5G, the release 16, release 17, and release 18, adding each time more and more features for positioning, with the goal that 6G approaches this target of 1 centimeter accuracy in indoor and urban outdoor scenarios. Because the areas of rural outdoors where the sky visibility is good in general, they are good covered by GNSS. Okay, I will present some basic mathematical tools that we have been using extensively in my group for analyzing positioning problems. And then I would talk about localization in 5G systems and in 6G systems. Okay, we have been using extensively the Kramerov bound and the Fisher information matrix. This is this is a bound. This is a tool that is very well known. But I just would like to remark that this tool is very useful not only for the analysis, but also for the design of localization system. The interest in bounds arise from the fact that they provide, obviously, a tool to do performance analysis, the ultimate performance analysis. They also provide information about the identifiability of the problem, whether the problem, the position, the orientation can be found or not. These bounds, the formulation of the bounds of the Fisher information matrix also provides information about the interaction between different parameters. So what is the effect of knowing one parameter on the estimation of the others? So this is useful to assess if it is worth maybe investing in a new sensor to determine one of the parameters, depending on what is the improvement that we will get in the estimation or in the quality of the others. So it provides also information about the dependency between the different characteristics of the scenario. So not about the parameters, about the characteristics of the scenario, like the number of antennas, the number of beams transmitted by the base station, the number of reflectors, the bandwidth of the system, and then it is possible to derive scaling law. So, and finally, it's obviously a metric against which the optimality of the estimators and algorithm can be checked. Just to mention that in the derivation of the Kramerov bound, usually we have followed a two-step approach where the signals, the scenario can be described by two sets of parameters. One are the channel parameters, which are also used sometimes in communications, that describe the signals received by the user with some parameters that are closer to the signals, like the delay, the frequency shift, angles of arrival, angles of departure. And then we have another set of parameters that we can that can describe the same scenario, which are the positioning parameters, like the position, velocity, orientation, clock offset, position of the receivers, etc. Usually, the camera bound can be derived in a two-step approach, where first the feature information matrix of the channel parameters is obtained. This is a relatively standard approach. And then using a transformation matrix, we can obtain the feature information matrix of the position parameters. This transformation only works in one direction, from the channel parameters to the positioning parameters, but not in the other direction. And this is the reason is that the position parameters is a more parsimonious representation of the reality. Usually you represent the scenario with less position parameters than channel parameters. So one can go from the bound of the channel parameters to the bound of the position parameters, but not the other way around. Okay, this two-step approach to derive the bounds is often also used in the derivation of the estimators of the position, orientation, and all the position parameters. The formulation of the estimators, it's in general very easy. The theoretical formulation, one can obtain the estimators, the maximum likelihood or the maximum a posteriori estimator. One has to maximize a given cost function, which is the likelihood. The problem that this is usually very difficult to implement in practice, because this function, it's very non-linear and very non-convex, so it has many local maxima. So these gradient searches or even grid searches, gradients can only be used if there is a good initialization point. And the derivation of a good algorithm to obtain these initial estimates, it's a bit of an art. It's not like the derivation of the bound, which is very systematic. Only one has to follow given steps. The derivation of a heuristic estimator of the channel or position of the position parameters requires some inspection of the problem, some understanding of what is the geometry underlying the formulas. And in this case, sometimes it's possible to obtain a position estimate with a very low complexity. As I said, the derivation of an estimator is a bit of an art. There is no fixed rule how to do it. Here I have a flow chart indicating what is a common approach, where starting from the waveform, one can apply a channel estimation algorithm and obtain some channel estimates. Then from the channel estimates, delays, angles of arrival, angles of departure, Dopplers, one can solve a geometric problem and obtain some coarse position parameters. This geometric problem can be very easy or very difficult, depending on how much insight we can gain into the geometry of the scenario. So from these coarse position estimates, we can obtain more accurate positions doing a gradient search. This gradient search can take as an input the channel parameters, or even go to the origin, which is the waveform. In this case, the methods are called direct position estimation, where directly from the waveform one can obtain the position estimates, or we can follow the most common approach, which is this two-step estimation, where we use the channel estimates as an intermediate step. Okay. Localization in 5G systems. Cellular positioning between 5G was kind of terrestrial replica of GNSS. In GNSS, we have a set of satellites that transmit signals, and the user measures the delay of these signals. In cellular positioning between 5G, these satellites were replaced by terrestrial base stations. So the user needed at least good visibility to 4 base stations. This made these systems not very attractive, and this is why it was never really widespread, except for fulfilling some regulatory mandates. The reason was that the infrastructure that is needed to provide this service is much more than the infrastructure needed to provide the communication service. For communications, you need good visibility to 1 base station. But for positioning, you need good visibility to 4 base stations. This means that the infrastructure has to be multiplied by 4 without a clear business case, because the operators or the carriers didn't have a clear idea how they could obtain income out of this. And of course, this was never very, very successful, at least to achieve good accuracies. Everything started to change when some 5G technologies become to be considered. This 5G, the initial key 5G technologies of 5G systems were a variety of carrier frequencies in the range of sub-6 gigahertz, millimeter wave, and also now we are considering also the band in between around 10 gigahertz. Large aggregate bandwidth, that could be in the order of 1 gigahertz in some cases, large number of antennas at the base station and also potentially at the user terminal, and then the use of side links and also higher network densification of these distributed cell-free massive MIMO systems. The two first items, this variety of carrier frequencies, in particular large frequencies, the large bandwidth and the large number of antennas, created a sparse channel. So the channel didn't have many strong reflections, only a few reflections associated to some objects in the environment. So there was a more tight relation between the channel, the electromagnetic channel, and the geometry. And this was a key point for positioning. Together with the availability of accurate time delay estimates because of the large bandwidth and accurate angular estimates because of the large antenna arrays. So this gives birth to the possibility of single base station, single snapshot positioning. And in my opinion, this is at the point where 5G positioning become very attractive to the research community and also to the industry, because with little infrastructure, maybe potentially only 1 base station, which is the same infrastructure that is needed for communications, one could also provide a positioning service. Okay, so intuition of why is this possible? We can imagine a 2D scenario where we have a base station here in the middle with an antenna array, a user terminal with an antenna array, and then there is only line of sight in this case, and then we can measure the angle of departure of the signal, angle of arrival, and delay. We have 3 measurements, but we have 4 unknowns. 4 unknowns, which are the position of the user, the clock bias, and the orientation of the user. Here we are in a simple case only on the plane. So we have 4 unknowns. Even if this is not a linear system, usually counting the number of measurements and the number of unknowns is a good indication whether the problem can be solved, is feasible or not. And in this case, actually, it is not. In this scenario, we cannot determine the orientation and position of the user. But if we add a reflector, even if the reflector is in a position that is unknown, we obtain this. Then we have this number of unknowns, 2 more than before, 4 plus 2, which is the position of the reflector, and then we have 3 more measurements because we have the angle of departure of this signal, the angle of arrival of the reflection, and the total delay. So we have 6 measurements for 6 unknowns, and actually this problem can be solved. And thanks to the presence of a reflector, whose position also has to be determined, the position of the user can be determined again. So in this case, it's clear that positioning also becomes a sensing problem, which are very fashionable nowadays, this localization and sensing. From the very initial point, localization with only one base station was also a sensing problem. One has to sense the environment to localize the user. This is only a qualitative way to prove the feasibility of the problem, counting measurements and counting unknowns. It usually works. There are more rigorous ways to do that. One is to come up with an algorithm, let's say, that shows that the position can be computed. So this is like a constructive proof of the feasibility, just to show that there is an algorithm that can obtain the position. Or another way is also to explore the Cramer bound or the Fisher information matrix. Here we had a paper where we tried to answer the question of what is the information that a reflector whose position is unknown adds to the system. And in order to do that, we have to inspect the Fisher information matrix. The Fisher information matrix, when you add reflectors into the system, includes more terms, because there is one term for each reflector, because each reflector adds measurements to the that the user can do, but also each reflector adds unknowns. So the matrix also becomes bigger and bigger and bigger. So every time when you have the Fisher information matrix of the line of sight, is like this. When you add one reflector, you have an additional term, but then the matrix becomes bigger because you have more unknowns. With a second reflector, then the matrix is bigger again, and so on. So computing the effective information matrix, the effective part, that say for the unknowns that are of interest, the position of the user, is not trivial, because it's not that this whole matrix what matters. What matters is the sure complement of one part of this matrix. Well, this was analyzed in this paper, and here it was shown that a reflector in the system contributes to the effective information matrix, to the FIM, with a rank 1 term. Rank 1 term that has this shape, has a scalar, and then a vector times itself, the outer product of two vectors. This is a rank 1 matrix. And the directions of these vectors are parallel to the, let's say, to the virtual wall that would generate this reflection. This reflection doesn't need to be generated by a wall, could be generated by an object. But in this object, on this object, one can place a wall that fulfills that the incidence and the departure angle are equal. So this will be like a virtual wall generating this reflector. And then the direction of the information provided by this new set of measurements is parallel to this wall. So this also is useful. This is useful to decide, for instance, where one can place reflectors in a given environment to increase the positioning performance. If you place reflectors in a given environment, you have to put them in such a way that the direction of the information that they add are orthogonal to each other, not all of them adding information in the same direction. This simple problem in 2 dimensions was extended to 6 dimensions, the 3 dimensions of the position, plus the 3 dimensions of the orientation in the paper that is mentioned here at the slide. Before that, many other papers, the references are in the paper, had been addressed simplified versions of the problem, whether the orientation was 2D and the position was 2D, orientation 1D. In other cases, the position was 3D and the orientation 2D, but the clock offset maybe was not considered, etc. In this paper, I think it's the first time that the full problem with position 3D the 3D coordinates are unknown, the 3 degrees of freedom of the orientation are unknown, it's solved. In this kind of problem, we can count parameters and measurements to have an indication whether the problem is feasible or not. The number of measurements that we have in this is 5 times the number of links, because we have, for each link, we have 5 measurements. 2 components of the angle of departure, 2 components of the angle of arrival, plus 1 delay. And then the number of unknowns that we have is 7. The 3 coordinates of the user, 3 degrees of freedom of the orientation, plus the clock offset. And then we have 3 times L, which are the position of the reflectors. We see that we have more measurements than unknowns when L is equal to 1. So when there is only one reflector that has to be sensed, the position and orientation of the user can be determined as well. Here is an example. In this case, when L is equal to 1, we have a problem with 10 measurements and 10 unknowns. If we want to solve this problem without understanding what is the underlying geometry, the problem becomes very difficult because it's a set of 10 nonlinear equations. But here I have an example of how a little bit of inspection into the problem can reduce a system of 10 linear a nonlinear system with 10 unknowns to a much simpler problem. In this case, we can think that we have the base station, and with the line of sight angle of departure, we can determine that the user is in this line here. I hope you see my mouse. It's in this line here. If we align the line, the angle of departure and the angle of arrival measured by the user, if we align them like this, then we determine already 2 degrees of freedom of the orientation of the user. There is 1 degree of freedom that is left, which is the rotation around this axis. This rotation angle can be determined doing only a 1-dimensional search, determining for which rotation angle the angle of departure of one of the reflections and the angle of arrival of the reflection close, or these 2 lines become closer to each other. These are lines in a 3-dimensional space, so they don't need to intersect necessarily. So we need to find the rotation angle for which these 2 lines intersect in a given point that would be the position of the reflector. Once this is done, we have determined already all the angles. So the only thing is that the whole figure can be scaled up and down because we have only used directions and angles. In order to determine the dimensions of the figure, we have to use the delays of the different paths. And then we can adjust a scale factor so that the differential delay of the reflected path and the line of sight path corresponds to the differential delay that has been measured. This is something that can be solved in closed form because it's a quadratic problem. So this means, to sum up, that this problem, nonlinear problem with 10 unknowns, can be solved with only a 1-dimensional grid search. So with only one nonlinear search around for this rotation angle. Okay, then after the initial estimates, one can do a gradient search, taking into account that the rotation matrix is not an arbitrary matrix, but is a matrix that belongs to a manifold. And then another topic that we have been working, and we think that is promising for the future systems, is the exploitation of the carrier phase positioning. Carrier phase positioning, it's a very well established technology in GNSS. It provides very accurate positioning, but it's also challenging because it's very sensitive to many errors in the measurements. This occurs because the carrier phase measurements are very precise, but they are ambiguous because carrier phase measurements they have an inherent ambiguity, which is the wavelength of the signal. Carrier phase positioning is the way to obtain centimeter level accuracy in GNSS. So the question is whether this can also be applied to 5G. Here I have a simple example of what's going on with carrier phase positioning. Imagine that we have only a one-dimensional problem where we have a base station and we measure the delay to the position of the user using the baseband signal, so what is usually understood as delay, which is a measurement that is not that accurate or is accurate as a function of the bandwidth and is non-ambiguous. And then we have the measurements of the carrier phase. The carrier phase measurements are very accurate but unambiguous. We can imagine that the PDF of the measurements is like this, very narrow, but separated multiples of lambda. So if we assess what is the positioning accuracy that we can obtain in this case as a function of the carrier frequency, we have a behavior shown by the blue line. It's a behavior that is not monotonic. It's not the typical behavior that we see in other type of analysis as a function of the power or carrier frequency or bandwidth. Here, it's very non-monothonic. We see that the performance improves when the carrier frequency increases, and this is because carrier phase measurements become more accurate, but at a certain point, performance degrades, and this is because lambda becomes so small that solving the ambiguity becomes too difficult. And it could happen that also there are so many errors in solving the ambiguity that the error of the position is higher than the error obtained using only the delays. So clearly there is a certain areas of frequency where carrier phase positioning seems to bring advantages, a lot of advantages. But for other carrier frequencies, this is not the case. I think, how much time do I have? Not much, right? Well, so this resolution of the ambiguity is a key aspect that makes carrier phase positioning feasible or not. So we can compare how much better, if it's the case, 5G systems are than GPS. The resolution of the ambiguity depends on the ratio between the carrier frequency and the bandwidth, because the carrier frequency determines the wavelength and the bandwidth determines the accuracy of the delay measurements. So the lower this value, the better. In GPS, this value is around 150. In 5G centimeter wave at 3 gigahertz, it's in the order of 30, and in 5G millimeter wave, it's in the order of 70. So these values are better than in GPS, but not even an order of magnitude, not drastically better. So one could expect better behavior of 5G, but not dramatically better than in GPS for carrier phase positioning, if we look only at this aspect. But there are two more aspects that determine the suitability of carrier phase positioning. The other one is the change of the scenario, because the set of ambiguous points change when the satellites move, in the case of GPS, or when the user move. And then this closing of the possible solutions, these closing points change with time. And there is only one that remains as the good one. So it is important that the geometry changes quickly, because this allows the user to easily distinguish which are the good sets of which is the good set of ambiguities and which is the bad one. So the change of geometry in GPS is given basically by the movement of the satellites, because they move much faster than the receiver. And the change of the so the change on the position or the angle with which the user sees the satellites, the angle basically depends. This is the velocity with which the user sees. This is the velocity of change of the angle with which the user sees the satellite. It's given by this value. But in 5G, the user, so in 5G, the base stations are static. They don't move, but it's the user that moves. Much slower than the satellites, because the satellite, they move at 5 kilometers per second, and the user maybe moves at few meters per second. But the user is much closer to the base station, much closer, in the order of 100 meters. This means that the apparent change of position of the base stations as the user moves is much faster than the change of the satellite positions. And this value is much bigger in 5G than in GPS. This means that the scenario changes much quickly in 5G than in GNSS. And this is very good, because this means that with very few epochs or with very few measurements, it's more likely to solve the ambiguities in 5G than in GNSS. The other main aspect for solving ambiguities is the probability of cycleless leaps. What we don't want is to have cycleless leaps in the phase measurements, because we want the phase measurement to be continuous, to have only an initial ambiguity, but then but we don't want the ambiguity to change between successive measurements. So this change of the ambiguity is what is called cycleless leaps, and it depends in many aspects. But one of the aspects that determine the probability or the difficulty of cycleless leaps is how many cycles the phase changes between two measurements. In GPS, measurements are taken every 20 milliseconds or even 1 second, and the satellite is moving very quickly. It's moving very quickly. This means that there are many cycles. The phase changes many cycles between one measurement and the other. So the probability of measuring this number of cycles wrongly is high. So we want this value, this ratio here, to be as small as possible, In 5G, the velocity of the user is much smaller. So this means that the relative change of the positions of the distance between user and satellite is much smaller in 5G than in GPS. And measurements are taken much more frequently, because the slot duration in 5G is much shorter than in GPS. This means that this ratio is very small, much smaller than in GNSS. This means that one of the main limitations that occur in GNSS, which is cycleless leaps, probably they are not present in 5G. So putting all this together, we see that 5G has a relative small advantage in terms of the ratio between carrier frequency and bandwidth with respect to GPS, but has a big advantage in the speed of change of the geometry and the probabilities of cycleless leaps. So this makes 5G positioning this makes carrier phase positioning apparently even more suitable for 5G than it is already for GPS. So this is a very promising technology. We have some results on this that I will skip. This will be presented actually in a paper in GlobeCom 2024, so in 1 month. And then I will just jump quickly to the 6G technologies. In 6G, we have additional technologies that could be have a very big impact in localization and sensing. We have the 5 previous key technologies from 5G plus 5 more. One is the well-known integration of sensing, localization, and communications that is sought nowadays to improve these services by exploiting the synergies between these 3 functionalities. The other one is the use of data-driven solutions for positioning using machine learning, artificial intelligence. The other one is the integration of the terrestrial network with the non-terrestrial networks, especially with LEO satellites. The ninth technology is an additional step in the network densification, which is the concept of distributed self-feed massive MIMO with phase coherence. So the possibility of having a large number of base stations around the user, which are coherent in phase, and then they behave like a distributed big, large array. And the other one is the shaping of the environment using intelligent reflecting surfaces. This is a topic, RIS, where we have worked a lot, and we have analyzed the advantages or the possibilities opened by these surfaces for localization. What is one of the RIS? This is well known nowadays. It's a small surface with a small passive element, so no noise is added. And the phase of each of these elements can be controlled. There are different types of reflecting intelligent surfaces, surfaces that only reflect the signal, as I said, with a phase that can be controlled for each element. Surfaces that refractive RIS, where the signal goes to the other side of the surface, and on the other side of the surface, it can be, for instance, captured by an antenna. There are signals that are surfaces that are both reflective, the third one, reflective and attenuating the signal. So this means that not only the phase, but also the attenuation factor of each of these elements can be controlled. There are hybrid RIS, where the signal is reflected, but also part of the signal appears on the other side of the surface and can be gathered by some RF change or combine several of them and put into an RF change. So the signal in each of these, in each or in a set of these elements can be processed. And also the RIS open different operating regimes because they are basically large. So the typical regime is the far field, where the signals, the response depends on the angle of incidence and the angle of reflection, angle of arrival and angle of departure. But as the signals, as these surfaces are large, we cannot assume that the waveforms are plane surfaces. We need to assume that the waveforms are spherical. So this creates this near field effect, where the response of the surface not only depends on the directions of arrival and departure, but on the actual position of the transmitter and the receiver. And also, if we combine the large surface with the large bandwidth that is usually transmitted in wireless systems, we also have wideband effects. This means that the response of the surface or the beams that are synthesized are not the same for each frequency. The direction of the beam, for instance, can change with the frequency. This is the known effect of beam squint. RIS are very useful for localization because they basically generate additional paths that can be controlled by the operator or by the user. These paths can be controlled in two ways, spatially, because with a set of faces here, the direction of the beam or the response can have a different, the beams can change in direction or can have a different spatial response, or can also be controlled in the time domain. We can also add a time modulation to the overall signal. And this aspect is key to distinguish the reflected signals, for instance, from the direct signal or from the signal reflected on other RIS or on other objects that don't introduce this temporal modulation. So also this allows us to have new measurements of the delay of this additional path and the angle of arrival of the signal and the angle of departure from the RIS. So the angle of departure of the RIS can be measured because the signal that is received depends on the profile of the RIS and the angle of departure. So changing the profile, one can infer what is the angle of departure. In the case of near field regime, the response not only depends on the angle of departure, but on the actual position of the RIS and the user, which is the RIS UE distance and angle of departure. If the RIS is hybrid, on top of that, we can obtain measurements on the RIS itself, which is the base station to RIS delay, and also the angle of arrival of the signal at the RIS and the angle of departure at the base station. So overall, the simple presence of a RIS introduces a lot of measurements that are available for positioning and measurements that can be controlled using the RIS profile and the time modulation of the RIS profile. And I think I will finish with this. I have run out of time, it's 1 hour exactly. Thanks to this, RIS can solve some problems that were originally unfeasible. So some localization problems that could not be solved without the presence of a RIS. One is like single antenna base station and single antenna UE localization. Okay. In this case, if the RIS is not present, of course, with one antenna at the base station and one antenna at the user, we cannot determine the position of the user. But if the RIS is present, the user can determine the angle of departure of the reflected signal, the signal departing from the RIS. So this determines that the user is on this line here. And then with the two delays, the delay of the line of sight and the delay of the reflected path, this creates an hyperbola. And then the intersection between the hyperbola and the line of the reflection determines the position of the user. So this time difference of arrival plus IOD from the RIS makes possible to determine the position of the user. We cannot even localize when the line of sight is blocked if we exploit, for instance, the near field. If the base station illuminates the RIS, but the line of sight doesn't arrive at the user, the signal reflected at the RIS has a curvature if we are in the near field, if the user is on the near field of the RIS, and then it can exploit the curvature of the wavefront to infer its own position. Then also, it's even possible to do self-localization without base station. This is a kind of inverse radar problem where the user is transmitting a signal and also receiving the signal reflected on the RIS. This requires, of course, full duplex operation. And here, the reflector, the position of the reflector, which is the RIS, is known. So it's not like in a radar that where the reflector has to be located. So this is why I say that it's like an inverse radar. But the user, with the transmission and reception of the signal, can measure the distance to the wrist with the round trip type of the signal, and then with the direction of the departure of the reflected signal, knows this direction, and then combining this direction plus the round trip time, the position of the user is determined. And also RIS can allow, for instance, for passive localization. Localization of devices like the cards here that they don't transmit or receive the signal. They simply reflect the signal. If we have a base station that transmits a signal that is reflected on the wrist of the card, the signal is received then by other receivers. These receivers, knowing the delay of the signal and also possibly the direction of the signal, can determine the position of the car. And this is this is well suited for a multi-user scenario, because each of the RISes can introduce a different type modulation of the signal, and it allows for the separation of the signals from the different cars. I think with this, these are more examples on some of the single antenna systems, zero base station localization, and exploitation of the near field. These are concepts that I have already explained. We had some papers for each of them. And I think with this, I will conclude. So the summary is that cellular signals have always been a source of position information, but positioning based on multilateration, so on the use of several base stations from which the delay is measured, presents several limitations. However, when high frequencies become available, also large bandwidths and massive antenna arrays, then the possibility of single base station positioning and sensing is closer to become a reality, and this changes the whole positioning scenario. And then positioning becomes much more attractive and maybe realistic in a practical cellular deployment. However, there exists still a gap between the current 5G capabilities and the 1 centimeter or less requirement of many use cases. The good part is that 6G introduces new elements to boost joint communications, positioning, and sensing. One of these elements is RIS, which provide additional controllable propagation path, a reduction of the base station or UE number of antennas required to achieve a certain functionality. They could even make possible positioning with zero base stations and also allow for the exploitation of the near field. Cell-free massive MIMO deployments also allow for the use of the overall waveform curvature, because they can be considered like a big distributed array, and then also make possible carrier phase positioning. The challenges are to make these models or these theoretical studies even more realistic with accurate hardware models, to make further investigations on cooperative positioning and sensing. Also, integrity, it's an essential aspect in many applications, because it's not only important to determine the position, but also to bound the maximum error that the position estimates have in safety of life applications or in critical applications where they are human life or big liabilities at stake. Integrity is metric that has to be provided as well. Signal design for integrated communications, positioning, and sensing. It's a hot topic. Further investigations on carrier phase positioning in 5G are needed. It's a topic that it's very promising, but it's in the infancies. And then, as in any other domains, the use of machine learning and artificial intelligence opens many possibilities. And last, to mention the extension of these terrestrial networks to non-terrestrial networks, which is a trend that we are seeing nowadays with the deployment of very big constellations by private operators, but also by the plans of states, of regions to deploy satellites to complement the terrestrial coverage. That's everything from my side.
Okay, well, thank you, Dr. Seco-Granados.
Yes.
Let's all have a round of applause for the very great presentation. Sadly, we have to hand over the room we are in, but I believe we still have time to take a question or two from the audience.
I can do that, yes, sure.
So, Dr. Seco-Granados, you mentioned the idea of using the near field for positioning. Yeah, but I have one question. How do you know that you're in the near field?
Yes. Well, I guess that there is many site information that you have in a practical application, no? You may know what is the dimensions of the RIS, what is which type of scenario you are operating, and maybe then only by the fact that you receive the signal, this also gives you some information of what is the maximum distance from which you are to the transmitter. So if you know basically the parameters of the scenario and what is roughly the distance or what is the maximum distance at which you are from the transmitter, you can determine if you are in near field or far field conditions. If near field or far field conditions is a purely, let's say, geometric condition, depends on the size of the transmitter and the distance to the transmitter.
Okay.
This is something that more or less probably you can know beforehand, depending on the type of system that you are operating.
Okay. Thank you.
Yes. Welcome.
So I have one more question. Has there been much work on like algorithm mismatch? By algorithm mismatch, I mean using the wrong algorithm in the near field, like you think you're in the near field, but you're not.
Yes.
So, has there been much work on the performance loss that occurs when you use the wrong algorithm?
You mean if we have analyzed that, or if I know? We have not analyzed. We have not analyzed that in detail. Okay. We have not analyzed that in detail. In our case, I think when there has been a mismatch is when, I mean, the cases where I've seen that there are some, let's say, mismatches and performance degradation is when you use the far field models and you are actually in the near field.
Yes.
In this case, yes. In the other case, when you use the near field models, but you are in the far field, actually you don't have a mismatch in the model because you are always, let's say, the near field models are also valid in the far field. The problem is that then maybe the conditions are not good to have good position accuracy, but there is no mismatch in that case.
Oh, okay. Thank you.
So,
That
yes.
answers my questions.
Yes. Thank you.
Okay, if there is no more question from the audience, I believe we will call it a day. A night for you in Barcelona.
Yes, actually, it has been a day. Yes.
Okay. Awesome. Thank you again. And you have a wonderful night. And thank you
Thank you.
everyone for
Thank you.
joining us today.
Okay. If you have any questions, you can also drop me an email, and I will be happy to answer. And yes, just to mention here, I already showed the slide. Also, I acknowledge my collaborators, Henry Mears in Chalmers, also Furkan Keskin, Kamran, in University of Salento, Alessio Fascista, Angelo Coluccia, in Technical University of Munich, Anastasios Kakavas and Joseph Nosek, and also the group of Klaus Witrischau, in particular Benjamin Deutschmann, Thomas Welding, and Erik Lichtenberg in Graz University of Technology. We have done papers with all these teams, and without them, the work would have not been possible by any means.
Okay, great. Thank you again.
Thank you. Bye-bye.
Bye.
Bye-bye.